On our next problem, we have f of x equals x squared minus 2x minus 8 over x squared plus 5x plus 6. And I want to factor that to see if anything cancels. So I have x minus 4 and x plus 2. On the top I have x plus 2 times x plus 3. So this is my factored form. But look what happens. X plus 2 divides out. And my reduced form is x minus 4 over x plus 3. Okay. So, because I have a different function, original function, than a reduced function, I'm going to have to be very careful about which ones I plug into. As a reminder, the only one that needs to use the original, now that we have an actually truly different reduced function, is the domain. So the domain is going to use the original. Everything after that, we're going to use the reduce function if we ever need to use the function again. So from the original, f of x, I'm going to set the denominator equal to 0, or really not equal to 0. So from the original, I have x plus 2 can't be 0, x plus 3 can't be 0, so x can't be negative 2, and x can't be negative 3. What is the domain? The domain is all the things it can be. So from negative infinity to negative 3, union negative 3 to negative 2, union negative 2 to infinity. Those are all the places where I'm going to have values. Now, the vertical asymptote is where we take the reduced denominator and set it equal to 0. The reduced denominator is just the x plus 3. I set it equal to 0, and I get negative 3. So my asymptote is x equals negative 3, and I can go ahead and put that on my picture. The next one is the wholes. If I have any canceled factors, I'm going to set those canceled factors equal to 0. The canceled factors, I have an x plus 2. The x plus 2 is my canceled factor. So I have x equals negative 2, so my whole happens at negative 2 comma some value. Well, how do you find the other value? Well, what I'm going to do is I'm going to evaluate f of negative 2, but I'm going to evaluate it at the reduced function. If you go back to the original function and you try to plug it in there, you're going to get 0 over 0, which is undefined. So you must put it into the reduced function to get the value of where the point would have been if it was defined. So I'm getting negative 6 over 1, or just negative 6. So at the point negative 2 comma negative 6, I would have had a point there, but I don't, so I'm going to put a hole. The hole means it's just not defined there. The horizontal asymptote, you find that by using your chart. And so I'm going to compare the numerator, the degree of the numerator. The degree of the numerator in the reduced function is 1. The degree in the denominator is also 1. So because they're the same, I'm going to take the leading coefficient, which is 1 over 1, and I get the horizontal asymptote is 1, y equals 1, and I can go ahead and graph that. I might have a point crossing the horizontal asymptote, so I'll want to find that out by taking my reduced f of x and set it equal to my horizontal asymptote. So let's do my work here, point crossing. So I have my reduced form, which is x minus 4 over x plus 3. I'm setting it equal to my horizontal asymptote, which is 1. I like to put my whole numbers as a fraction so that I can cross multiply. I get x plus 3 equals x minus 4. When I solve, that gets me positive 3 equals negative. No x's left. Okay, so if there's no real x's left, you can't have a real solution, so therefore there isn't any point crossing the horizontal asymptote. To get my x-intercept, I'm going to take the reduced f of x and set it equal to 0. So let's do the work over here. So my reduced function is x minus 4 over x plus 3. I'm going to set it equal to 0, And then I can cross multiply. I get x minus 4 equals 0. A faster way of doing that would probably have just been to set the numerator equal to 0. And the last one is to find the y-intercept, which is always 0 comma something. In this case, to find the y-intercept, I'm going to evaluate f of 0. That turns out to be negative 4/3. Okay, so I'm going to plot my x-intercept at 4 comma 0. I can also plot my y-intercept at 0 comma negative 4/3, which is negative 1 and a bit. And all of those points together are telling me that my branch on the right-hand side of the vertical asymptote is below. Okay, so now I'm not sure what's going on the left-hand side, so I'm going to have to plug in a point. I could use a little bit of deduction here. I know that there's only one x-intercept, so I doubt that it's possible that the graph could be below here, because it would at some point have to cross the x-axis. And because I know it doesn't cross the x-axis, my big guess is that it's above the horizontal asymptote. So to be sure, I'm going to plug in a value that is to the left of my vertical asymptote, so I'm going to plug in negative 4. So I evaluate f at negative 4. Again, I always like to use my reduced function. The only one I don't use the reduced function for is the first one domain. So I'm getting negative 8 over negative 1, which is positive 8. So at negative 4 comma positive 8, I've got a value. That one value with the asymptotes tells me the rest of the picture. And that's a pretty good graph. For our next function, f of x equals x squared minus 1 over x minus 2, the numerator can factor. But the numerator and the denominator don't have any common factors. So therefore, the reduced function can either be the factored form or the original function. There is no real new reduced form. So let's go ahead and do our problems here. For the domain, I'm going to set the denominator not equal to 0. That's of the original. So I set x minus 2 not equal to 0, so x can't be 2. But when I answer the domain, I'm answering it in interval notation, negative infinity up until 2, union 2 to infinity. Those are all the values that I can have. For the vertical asymptote, I set my reduced function, denominator, equal to 0, which is basically the same as the original since there's no new reduced one. So x is equal to 2. There are no holes because there are no canceled factors to set equal to 0. To find the horizontal asymptote, I use the chart where I compare the degree of the numerator, which is 2, over the degree of the denominator, which is 1. Because the numerator has a larger degree, the horizontal asymptote, well, there just is no horizontal asymptote. So therefore, if there's no horizontal asymptote, that means there can't be any point crossing that horizontal asymptote since there's no horizontal asymptote there at all. To get the x-intercept, I'm going to set the numerator equal to 0. That would be of the reduced one if I had a reduced form. So to get the x-intercept, I'm going to take the numerator, which is x plus 1 times x minus 1, set it equal to 0. So x is equal to negative 1 or positive 1. So I have actually two x-intercepts, positive 1 comma 0 and negative 1 comma 0. And the y-intercept, I'm going to find that by evaluating the function at 0. So f of 0 is going to be 0 squared minus 1 over 0 minus 2, which is negative 1 over negative 2, which is positive 1/2. Let's go ahead and plot everything that I have. I have a vertical asymptote at 2. I've got 2 points, one at negative 1 comma 0 and 1 comma 0, and I've also got another y-intercept at 0 comma 2. Because I have no horizontal asymptotes, this isn't going to approach any line horizontally, but it will approach vertically. So I know that my line has to touch these 3 points and it has to get really close to the vertical asymptote. So I know that much. I suspect it's going to keep coming down, but I'm not 100% sure, so I'm going to have to find some more points. So in order to find out where this graph goes towards the left, I'm going to plug in one more point. I'm going to plug in -2 because that's to the left of the points that I already know. So I'm going to plug in -2. I'm going to plug it into either the original or the factored because there is no reduced to use. If I could have used a reduced, I would have done that. So here I'm getting 4 minus 1, that is 3 over -4. So -3/4, which is telling me that this is going to keep going down. Okay, so now I'm going to have to figure out what's going on to the right of 2. So I'm going to plug in a couple points because I can't keep approaching some horizontal asymptote since there isn't a horizontal asymptote. I'm going to need a lot more points to figure out what's going to happen here. So I'm going to try f of 3, f of 4, f of 5 to really get a good picture of what's happening. So I have 9 minus 1 over 3 minus 2, so that's 8 over 1. 16 minus 1 over 4 minus 2. I'm getting 15 over 2. And the last one, 5 squared is 25 minus 1 over 5 minus 2. It's 24 over 3, which is 8. So at 3 comma 8, I have a point. At 4 comma 15 halves, 15 halves, that's 7.5. And then at 5 comma 8, going back up again. So I know that my line is going to approach my vertical asymptote. It's going to come down, turn around, and kind of go off in that direction. And that's a pretty good picture. Now we don't talk about any other asymptotes other than vertical and horizontal, but when you get to pre-cal, you're going to learn that there's another type of asymptote here, which is called an oblique asymptote, which kind of goes at an angle. And that's the kind of asymptote that this problem has. We didn't actually know that from what I've taught you so far, but we just had to plot a whole bunch of points so we could find out which direction it's going. But it's interesting to note that there is an asymptote there. It's just we're going to cover that when you get to pre-cal.